Okay, so welcome to the second talk of fall 24. So given again by faculty in our group, Dr. Shi Bai, who's going to talk to us about lattice-based cryptography and a bit of his research, I suppose.
Okay. Thank you, Francesco, for the introduction. So, the title I'm going to give a very brief introduction to lattice-based cryptography, together with some algorithms for breaking it, as well as some construction, just to get some ideas of how this thing looks like. So before I start, I want to mention that like usually we call it the way of proving the security of public key crypto system, right? You have heard about encryption schemes and signature schemes. They all have different functionalities, but how exactly we show that these schemes that we constructed or we use in practice are hopefully secure, right? So the general idea is it's done by a formal proof, which is exactly like a mathematical proof. It's a rigorous proof, and then essentially what happens is the security of public key crypto system is based on some conjectured or believed hardness of certain computational problem P. So I emphasize that this is conjectured or believed. The only reason is so far all the mathematical assumptions used in cryptography or that we can prove that as the underlying security for crypto system is only conjectured. They have not been showing that they are in NP hard or NP complete. You may have found some literature saying that, okay, some crypto system is relevant to a NP hard or NP complete problem, for example, even for lattice. But usually what happens is that the parameter that we have for this, according to this mathematical proof, does not allow us to have NP complete or NP hard problem. That's why I'm saying so far all the mathematical problems based on public crypto are conjecture or belief. For certain computational problem, here I just give it a simple name. I call it P. For example, it can be the integer factorization problem, which is quite famous. Okay, and here is really a blueprint for the security proof for a cryptography scheme. So how do I exactly prove? How does this mathematical proof exactly work? For example, for encryption scheme. Okay, so the way that we do is just do like a positive proof, assuming that there exists an efficient algorithm that breaks the security of an encryption scheme, for example. Then somehow I can turn this efficient algorithm, or that's what I said, we can leverage this algorithm that solves some related problem P efficiently, also in polynomial time. So basically it means that if I can break the encryption, I can break the underlying problem. So that shows what? That shows that the encryption scheme that you are considered is no weaker than the underlying mathematical problem, right? So basically, the way that we are writing this is to say there's a problem P, this is the underlying math problem, reduces to that's just the symbol, which is popular in this area, shows that shows this procedure and to some scheme, right? Which the scheme. For example, this can be an encryption scheme. And again, this jargon just says that this is just example. Okay, this just means that if I can break encryption, I can turn this algorithm of breaking encryption into an algorithm for breaking this P. For example, this can be a factoring problem, right? Just as an example. Okay. And this also shows that the scheme that you have constructed is no weaker.
Do you also have the reduction on the other side of the scheme?
The other side is open, obviously, but I don't know whether there is I don't know whether there's a canonical relation that I can always show that the other. But you're right. Usually, what happens is if I can break the problem for P, I can almost always break P. Yes.
And this P is considered to be the harder problem?
P is considered to be the conjectured hard problem. In mathematics, for example, it can be a factoring problem, it can be a discrete logarithm problem, can be a code-based problem that Edward introduced last week, can be a lattice problem for today. Yeah.
So what could be the counter example of that other way?
I don't know. That's why I'm saying I don't know whether it. I feel like it always works like Edward said, but I don't have a formal proof at this moment.
Or they probably just need this sign.
I think what he's saying, I agree. Usually the way you design the scheme,
Yeah,
immediately it's broken if you can solve that.
yes,
problem.
yes,
What is hard to show is that the other way around, like,
yes,
Even,
yes.
even for RFA, I think the RFA form is not shown.
No, no, I agree. Yeah, yeah. It's only the reduction is, so basically the example I had over here for factoring was probably not a very adequate because there's exception for factoring problem that we don't have such reduction, I believe, right? Yeah, it only reduces to the ISA problem, not the factoring problem, I think. Yeah, yeah. But that's the general idea. So basically you show that the idea is that the idea of this proof is essentially to say that you need to have I wouldn't say higher power, but you need to have a equivalent power for breaking the scheme compared to breaking the mathematical problem. That shows the hardness of this scheme. Okay, and of course, immediately after that, I'm going to give a list of computational problems that has been currently used in PK, in public key crypto, and they're actually used in practice. For example, like this integral factorization problem. There are discrete logarithm problems, DLP over P where P denotes the prime field, and there's a discrete logarithm problem over a finite field where this Q denotes the characteristic. It can be very small. It can be up to prime P. So basically something which generalize this. And there's also elliptic curve discrete logarithm problem. If you look at their status for the classical algorithms, we already have a substantial algorithm for integral factorization, and we also have substantial type for DLP over prime field, where the running type, where these two substantial roughly have this about 2 to the n to the 1 over third with some extra log n c, where n is the number of bits of the problem. For example, it can denote the number of trees for the underlying prime field tree. But for discrete logarithm over prime field over finite field of small characteristic, there are even Cauchy polynomial algorithms which are very close to polynomial and up to substantial depending the characteristic relation with respect to the n. And also for ECDLP, so far we classically we haven't have the full exponential algorithm. Full exponential, to some constant type n. And usually what happens for crypto, this constant is usually smaller than 1 for many of the algorithms. So this boils down to the question of how do we set up the concrete parameters, right? But so far this four or this at least this we can characterize as integral factorization, DLP and ECDLP. I think especially the integral factorization and ECDLP, they are very popular and they are used in practice. So the way I always show this is that you can actually see them. You probably see them where if you just get to any website, and then if you click this log C, I'm not sharing. Yeah, basic.
Yeah, for Zoom.
Yeah, for Zoom. I don't think I can share too, but
You can share the screen.
okay, I see. Okay, great. So basically, if you get a browser, let's say I get onto Google, if you click this thing, and then if you just do maybe more, no, maybe here. So actually, maybe it's this cookie data that happened here. No.
This is cookies.
Permission for this site.
In this browser is.
Yeah, so usually I knew how to do this, but I just couldn't find it here anymore. Usually where you can find the actual what is this browser? Edge, right?
Do you have another browser in there?
Yes, I think I am more familiar with this to show this. It's just they probably hide it somewhere. But this I think it's
No, it's connection security.
It's probably hidden under that talking with the 3 dots, which would be.
oh here.
The
Certificate.
black box.
Yeah. Yeah, basically, if you look at this, you can check the details and you can see some algorithm, right? Public key algorithm.
That's a public.
Yeah, so you can see this user elliptic curve was probably depends on ECDLP. And there's usually another something called, so this is a symmetric key. There's also a certificate, so you can see this. I think there's a hybrid, but it says that it uses some RSA encryption to send some symmetric keys. But anyway, so this is where you can actually see the name of the algorithms. I think I'm still sharing, right?
You try to do this for some really small, insecure website and see. Because Google, I believe, they're secure, but you should.
Right. We can develop it, right?
Yeah, you should check the FAU side.
No, actually, we should check our method because I always remember sometimes the certificate was not verified for something. But anyway, so in terms of quantum attacks, there's this famous paper by Short, which says that you can break all of these assumptions in polynomial time, and that polynomial does not mean it is easy because it depends on the quantum resources that you require, right? But people have been inventing new algorithms try to reduce the quantum resource needed, and of course, so this is based on the assumption that a sufficiently large computer with that kind of resources can be built, and the physicians, I think, physics people are still working on this for the moment. But again, to prepare this, we need a quantum resistant crypto, right? This is usually called post-quantum crypto. So there's lots of candidates in terms of mathematical assumptions. Dr. Petruccetti talked about this code-based crypto, and there are also group-based crypto, hash-based, assorted-based. I'm going to focus on this lattice-based, but there are also multivariate-based. So there are several different mathematical assumptions, several categories of mathematical assumptions that you can use. So sometimes these assumptions are some sort of related. So their forms are similar. But anyway, I'm going to focus on a quick introduction of lattice-based crypto, which is believed to be, at this moment, hopefully believed to be secure against quantum computers. Again, I would like to go back to the first page and just saying that so far, believe just means this is conjecture. So we are conjecturing that there is no quantum algorithm for breaking, there's no efficient quantum algorithm for breaking lattice problem, but we didn't rule out the possibility that there is such an algorithm. Okay. This is true for anything, for all the other categories as well. Okay. So what we will use in the construction is the so-called Euclidean lattices. And we will usually consider an integral lattice where all the representation are integral. Okay. So starting with, for example, an linearly independent vector B of I, the n, and then a lattice generated by this B1 by this vector B1 to Bn is simply the integral linear combination. So it's really just the linear span of these BIs. The only difference is that we impose a discrete geometry here by saying that I only allow integral linear span. That's the only difference. So it becomes a discrete set of points. I'll give a toy example, and I will use this toy example, the wrong example. For example, take n equals 2, and I pick up two vectors B1, B2, where it has this form, right? So the lattice is simply the set generated by the integral linear combination of all the points. So basically, I have a Z1, which is the arbitrary integral coefficient, times this vector B1 plus Z2 times this vector. So clearly, we can easily just think about several points. We can take Z1, Z2 to be 0. So the 0 is always a point. 0 is always a point. 0, 0 is always a point in the lattice. And of course, I can choose Z1 equals to 1, Z2 equals 0. So B1 is in the lattice. I can choose B2, Z2 equals 1, Z1 equals 0. So B2 is in the lattice. But I can also choose both of them equals to 1. This means that their addition, which is I got 1 and 6, which are in the lattice. And if you do this for all the Z over here, it generates the full the full lattice. So that's exactly the question I had. So just trying to give another notation just from linear algebra. Instead of using this one, I can rewrite, I can combine B1, B2. So remember that I'm using the column form over here for vectors. So basically you can combine the two column vectors B1, B2 as a matrix and move the Z1, Z2 as the coefficients. And that's how I get this form, right? So these are the, this 4, 2 is the first vector, minus 3, 4, 4 is the second vector times the coefficients. So the lattice generated by this basis B, where this basis B is the column form matrix by all of these basis vectors, B1 to Bn, that's it. So we usually call these the basis for such lattice, where it has the same meaning as the basis, almost has the same meaning as the basis for linear space. And there are, of course, there are infinite number of bases for the same lattices, and you can use the so-called unimodular transform to get another one. The volume of the lattice is exactly, this one is exactly the same as the linear algebra from there, which is the determinant of this B. And this is independent of the choice of the basis for the lattice. Just some basic stuff. And let's draw this lattice. That's exactly the lattice I think generated by this one. Because if you count down, this is a two-dimensional thing. If you count the first vector, which is 4, 2, so I have 1, 2, 3, 4, and I have 2. So that's one vector. And the other vector is minus 3, 1, 2, 3, minus 3 to the fourth, 1, 2, 3, 4. So I have this point. So basically, that's why I emphasize these two vectors over here. And it's a linear, it's a discrete, or it's an integral linear span. That's why I don't include anything in between. It has to be integral combination. So all of these three dot points are the of this particular lattice. So that's exactly the definition. So after we define the lattice, the most important thing relevant to crypto, of course, is what are the natural computational problems on lattice that can be used for crypto. There are lots of computational problems, but the most relevant one, which is relevant to this quantity, which is called the lattice minimum. So given a lattice, the lambda 1 is a function defined on lattices, essentially extract the minimum value of the L2 norm. So all the norms here are Euclidean of a non-zero vector. And for example, in this picture over here, I'm excluding this zero vector, and it's visually it looks like that this vector is giving me the shortest length, right? So, so if I draw a sphere using the radius dot, it actually verifies this because within this sphere there is no other green dot points other than 0, 1, and it's on the boundary, which means that indeed this vector and its symmetry correspond to the shortest vector of this lattice. The shortest vector of lattice is not necessarily unique, already giving the two-dimensional picture over here. So now the shortest vector problem is defined the following way. So the input B is just, for example, right? Our two-dimensional thing is just a matrix. It corresponds to the basis matrix for some underlying lattice. And this B given in the cryptography is actually explicit. You're given this input. The question is to find the V such that admits or which admits the lambda 1. So find the what's the shortest vector from the lattices. So the difficulty actually heavily depends on the shape of the input basis B. So it also depends on what sort of lattice you have. But what happens in practice is that people are more cared about changing the shape of the input basis B such that a bad B is given. So visually, I'm going to give this example. So for example, what is the shortest vector in this following basis? Again, this is column 1. Right. So this was not so obvious just from this one because the two vectors seems to have a big R2 norm. But if you just recover this, of course, I created artificially. If you time this coefficient and you do the recovery, you can see that actually it recovers the vector 4, 2, which was somewhat short in the previous picture. So actually, this lattice over here is really just another basis for the previous lattice, and you can check the determinant or unimodular condition. So they exactly correspond to the same lattice. And this phenomenon can be described by this picture visually. Assuming that this was the basis vector that I showed before, this wasn't really like the previous two-dimensional picture. But it looks like there are two vectors which are reasonably short. So they simulate the case where I have 4, 2, and the other is -3, 4, right? They're relatively short. But I'm not going to give this B. Instead, I'm going to give this B over here. And so visually, this would correspond to this case. So which is the right one and the blue one, which again, I claim is the basis by the way how I draw it, because I use a computer system to draw it. And these two are, and I guarantee that these two vectors over here are linearly independent, and they essentially get exactly the same green dot point. That's why I didn't change the green dot point at all, right? So the question is, if you see these two vectors over here, how do I figure out the shortest vector, or how do I recover these two vectors? For example, numerically, if given this, how do I know that it corresponds to it gave me like 4, 2? That's exactly the difficulty of this C. And in practice, the dimension of this lattice has to be very high for the computational hardness. For example, usually the dimension of the lattice is at least 500. In some other applications, for example, in homomorphic encryption, the dimension can be up to like a few thousand or even 10,000. That's quite popular. Okay. Just trying to think about this problem. So I introduced what lattice is, and then what is the computational problem. We haven't talked about the application, which is something that I'm going to talk about after this. But let's think about the best algorithm for solving this, just from a brute force or combinatorial point of view, right? So there is an enumeration algorithm, which is quite simple. I will just mention this, which runs in 2 to the big O, basically the constant over here, that has n log n. So it's a slightly super exponential time, because there are 2 to the n is single exponential. There are log n, so that's why I call it super exponential. That's one of the algorithms for solving the problem, where n denotes the rank or the dimension of lattice. And there's also another class of algorithm, which is called sieving, which takes 2 to the big O n, which is single exponential. At least both of these algorithms, where it's clear that the sieving algorithm is faster than the enumeration, right? Because there's no log n factor. At least both of them, just because this enumeration only uses polynomial space, where this sieving also uses exponential space. So it also uses 2 to the big O n space. So this enumeration algorithm is very simple. So I can just introduce it in a few slides, just to give some idea is how hard it is to break this, or is there at least a naive algorithm that can break it? Okay, this is just a notation where I denote this Bi star as the Gram-Schmidt oscillation of B, just for convenience. Okay, so and here is the enumeration algorithm. Assuming that I knew a good upper bound for the short vector of a lattice R, and this R, we usually have some good practice. We usually have some good estimate, both in theory and from practice. So the idea is to enumerate all the lattice vectors, all the non-zero lattice vector V, such that the norm is bounded by R, and we just pick out one of the shortest ones, right? So, so the only change that we will do is instead of using the BI, we just change it to the orthogonalized, to the GSO basis, because then we have the orthogonality. That's easier for us to bound the norm, right? Because we can separate the norm inside each of the individual components. For example, assuming that V corresponds to some hidden short vector, where V can be written as an integral linear combination of Ci Bi, and Bi I can rewrite this as using the Gram-Schmidt, right? So I just expand this using the definition of the Gram-Schmidt, where each Bi equals to this Bi star plus this mu, which are the coefficients for the Gram-Schmidt, and Bi star. And then I can rewrite in this form, and then I will take the norm, square norm from both sides, and the square norm gets into the can be actually breaks up into the each component of Bi star, and therefore I have a summation of the square norm of the Bi star, right? So if you read this coefficient carefully, you can see that I can take the last part of this because I have the orthogonality condition. For I equals to n, I can take the corresponding part for I equals to n, and that's exactly this part because there are no cases larger than n, right? So really the last part is really C of n times B of n star. Of course, I'm taking square norm. So I have C squared B square norm smaller than the bound R squared. And this condition is already sufficient for us to enumerate all the possible choice for Cn, right? So basically, this algorithm, maybe this algorithm is not clever enough because it has to exhaustive search all the Cn for this step, but at least it will not miss anything, right? It will output all the Cn satisfy this condition where Cn corresponds exactly this C. Here. And what happens is for each of Cn, so I'm going to draw a picture. For each of the Cn, for example, I can got 3 Cn, right? It's possible that I get 3 of them. For each of them, I'm going to fix this. For example, I'm going to fix this one. And after I fix this, I will consider the second term from the bottom, which turns out to satisfy this, which turned out to be exactly this part. So my Cn in right column is already fixed from this step. So this corresponds to the Cn. And then the algorithm will go backwards to search all the choices for Cn minus 1, right? Everything else is fixed. The Cn, mu, B, and the Cn, they're all fixed. So I can find out a permitted range for Cn minus 1. So for example, if I fix this C1, there might be a permissible range for Cn minus 1 for each of these. And then maybe I'll fix this one. I'll do this tree search. I can have another range for Cn minus 2. And of course, this is only one branch of the tree. If you consider all of this maybe gives something like that. And essentially, the running time of the algorithm is to estimate how many nodes are on the tree, which uses some geometry of this Gram-Schmidt. So for example, in order to estimate how big Cn is, you can just divide this R by this Bn star, right? As long as you have a good estimate for the shape of Bn star, you would be able to get some estimate for Cn. That's very similar for Cn minus 1 because everything else is fixed. It only depends on the geometry of Bn star and the Bn minus 1 star. And that's how you get the running time, which is about which is 2 to the n log n over here. Basically, this algorithm is so simple that we can just introduce here. Okay, that gives some idea of how to solve this SVP problem, right? So we introduce a problem, and then we consider some algorithm to do this. There is a further question is that remember that the previous picture I showed you that there was a case where my input basis was really bad, right? For example, my input basis is this one, and this was a good basis, was a bad basis. But in the actual application, how do I guarantee that the problem that can be reduced to, or which can be related to, has to be in this shape instead of that shape, right? There's going to be a formal way to do this, and this is the so-called by the so-called worst to average case reduction. So instead of directly using this SVP problem on the lattices, we also define some intermediate problem, which is the so-called average problem. So instead of having the full picture that I mentioned, I have some problem P to this scheme, I insert another problem, So this P was usually, in this case, for example, it can be related to the SDP that I described, and it has this chain. And there is a problem which is called, for example, LWE, which is usually so-called the average case problem. The average case problem just means that you can easily sample. So there's a difference. So you can easily sample. And what is guaranteed is that if you sample a random instance of the LWE problem, it is guaranteed that this is no either than an arbitrary problem in P. This is usually called the worst case for average case reduction. And that's why we need the help of this average case problem. And the average case problem is very easy to describe as well because of this randomness. You can easily generate some. You can have a very easy distribution. For example, for this matrix form of the so-called LW or learning with error problem, actually, the reference is on the title, but I don't know. You can see that. But anyway, it was given by Ricky back in 2005, 2004. What we use in practice is usually the so-called matrix form. So for example, we have some modulus Q here, and we have some integral dimension M and N, and we sample a uniform matrix A. This distribution is very easy to sample, right? It's a uniform distribution from some, for example, from some underlying field. And we also sample a secret vector S according to some distribution ds. And this distribution can be uniform distribution as well. I just didn't specify here because there are several positives. What is really important is that another vector we call it error vector, and it has to be small in the geometric sense. It has to be small in the Euclidean norm. So this corresponds to essentially in the code case or in decoding case where you have a small Hamming weight actual error vector E. But here the small in lattice is usually defined by some geometry, for example, by the Euclidean norm, according to some other distribution E, DE. So the problem is really similar to the decoding problem, where you given A and B, and where B equals to AX plus E. So the only constraint is that E has to be a short vector in some geometry. So the question is to recover either S or E. And for the problem, for example, if I recover S, of course, I can compute B minus AS equals to E. And if I recover E, there's going to be some condition A, make sure that I can recover S, which basically means the solution for S is unique. And for this to be true, we usually require the parameter M to be larger than N to some scale. And therefore, I have the following sort of standard parameter where my N is about the same of the lambda, where the lambda is security parameter. For example, I want the scheme to be 128 secure. I can choose my N to be a constant times 128. For example, 5 times 128 or 10 times 128. And my modulus Q is usually N times the constant, for example, N to the constant. For example, Q can be N to the square, right? Can be a quadratic thing. And then my M has to be slightly larger than N, as I mentioned before. So I got a tall matrix. So M can be N log Q. DS can be a uniform distribution, same as A. And the DE, to guarantee that this E to be small, DE has to be somewhat small. And there are some parameter alpha, which usually is called the error ratio. But it doesn't matter, it just say that alpha times this Q, this parameter alpha times Q is the standard deviation for this correspond to this discrete Gaussian. For example, the deviation is about the square root of N. And if you're thinking about the case, the whole system, this equation is defined modulo Q, where Q is N squared, but I require the geometry of E, like the norm of E, to be about side of square root of N, so which is smaller than the Q. So most of the if you consider computing this in practice, A is uniform Q, S is uniform Q. So if you multiply them together, you get something which is be larger than Q, right? So there will be something modulo Q, will be writing around Q. But after you add this E, this thing AS modular Q will not be further modular another Q with high probability simply because this E is small. Okay, so that's what happened for the underlying arithmetic. Okay. Again, this is to solve a system of non-linear equations simply because this actual E. If there's no this E, this problem is simple. It's trivial because you have B equals to A times S. That A is a top matrix. High probability is over determinant. So you can solve this problem using linear algebra, which is trivial. But adding this E and all the uncertainty for this A times S, so there it becomes non-trivial to solve. The problem I mentioned before is called the search version. So given A and B, we are asked to find either S and E, and it's equivalent to find either of those. But the insecurity proof, like the proof I mentioned before over here, right? So if I want to prove that LW reduced to a scheme, we usually use this decision version simply because it's easier to use to complete these proofs. So given samples A and B, where we don't know whether they are generally LWE samples or they are truly uniform random samples over the underlying field. And the task is to distinguish whether it's LWE sample or they are from uniform. So the problem, the decisional version looks like a little bit strange, but it's quite useful in the proofs because it's very easy to simulate them in these proofs. Okay. Another problem that we need to use in order to introduce the crypto system, because so far I haven't introduced anything about how to use this to construct crypto, right? So we need another problem, actually, another sibling problem, which is called the matrix form of the ISIS, which is for short as inhomogeneous short integer solution problem. Again, I have several parameters and a distribution DE, and this DE you can think about it has the same as the E in the RWE. So the idea is to sample a uniform B, and for this B, you can think of it as the transpose of the A. So because I change the two parameters and N to N, that's very important to make sure the ISI problem is well defined. So it's a wide matrix B, and I sample a small secret E according to this distribution DE. In the next step, we are given B and T, where T equals to BE. The idea is simply to recover E. Right? So it's like a syndrome decoding problem from the code-based crypto, where we are given the blue plot, we are given B, we are given T. The idea is to recover this solution E. So alternatively, you can think about this vector version of the so-called knapsack problem, where in knapsack, you are giving a single row and the time this secret E equals to a single value. So you can think about this as the vector version for that, where B is let's see. And again, E has to be a small thing for this thing to be well defined. Again, so far the best algorithm to solve this C is to the big O(n), which is the sealing algorithm. Okay. Okay. So now we have seen the LWE problem. We have seen the SVP problem, right? So for example, we have seen the SVP problem, and we know the time for solving that. We see some problem in the middle, which is called LWE and CIS over here. But so far we don't know how does this work, right? So this is going to be focused on the next few slides, where we're going to construct a scheme using this. I'm going to focus on maybe on the security, and to just give some rough idea of why it's secure. Okay. So in public key crypto, there are the private key and public key. So in this case, my S, I'm going to take a matrix S, right? So instead of vector S. And I will compute T equals to AS plus E. This is exactly the LWE thing I mentioned before, where I have B equals to AS plus E. The only change is instead of having a vector S, I have a matrix S, and therefore correspondingly I need to have a matrix E, and then I have a matrix T. That's the you can show that this is equivalent to this is no weaker than the LWE problem with that simple columns. Okay. All the parameter setup are very similar to before. The only thing I refer is E is small for the problem for the function for the encryption scheme to work. Okay. The public key is T and A. T is like our B before, and A is the matrix. So I have a big remark saying that this is the LWE assumption. Make sure it's secure. Okay, now I want to encrypt some message n where I assume that it is a small vector, small in the sense that its infinity norm is small. For example, it can be a binary vector. So to start with, I'm going to choose a small random vector R over here. And I will compute the ciphertext, which consists of two parts. The first part is U, which is equals to AT and R modulus of underlying modulus. Remember that A here is a tall matrix, and therefore A transpose here is a wide matrix. So a wide matrix times a randomness R exactly is our cis assumption. So this part would be secure because of the cis assumption that we mentioned before. Remember, this was the picture, right? B times E, B is a wide matrix, and this B is essentially our A transpose here. So this one. And the second part of the ciphertext is this one, is C equals to this big T transpose times R plus M over here. That's the second part of the message. And you can actually show that this T, so this T over here, depending on the parameter, but usually it's going to be a tall matrix. You can think about this T as a wide matrix. So you have a wide matrix times R, again, it's a cis problem, plus some M is also uniform. So that's the general idea of the security. So what's left over is, if we assume that we send the U and C, they should be secure because of these two assumptions. But how do I decrypt it, right? So how does the decryption work? So the decryption works with the secret key S. And so the idea is, given UC, how do I use S to recover this message N? And you can check the equation, the following equation. They are all in matrices, so that either works. So I have C minus S transpose times U. So C is part of the ciphertext, right? U is also part of the ciphertext, and S is the secret key. I just do a secret matrix. I just do a transpose, make sure the dimension matches. So C, I'm going to plug in with the T to the TR plus N, this part, minus ST times U, which is ATR. So that I literally copied it in here. And of course, now I'm going to plug in the definition of T. T equals to AS plus E, therefore T transpose, this part, equals to S transpose A transpose plus E transpose, so I have this part. And then plus, so that's the E transpose times R here, plus the leftover, which is M minus this. So the main idea of this big part SAR is cancelled with this SAR. And therefore, what's left over is only ET times R plus M. And that's where we need the smallest come into play. Because at this moment, I only have this part in the middle, ER plus M. I'm hoping that this ER plus M is approximately the same as M. So I can drop this. So in a naive way, you can think about this. Maybe I can multiply this M by some scaling factor to embed M to the most significant bits, and then this ER corresponds to the lower cases. So if I do a dropping, if I drop the least significant bit, it will throw away E times R and left over with the M. That's exactly the idea how the LWE-based encryption works. And this is also why people saying that in lattice-based crypto, there's usually a decryption failure. And this decryption failure usually corresponds to this decoding capacity. If you think about this step, I have N plus some error. I want to recover the message. You can rephrase it formally as a decoding problem, right? So basically, it depends on the code that you use here. Okay, so any question for this scheme?
What is important? Is there a name?
Yeah, so this is LW-based encryption, but there are two forms. One is, so what I described here is the public key is using LW assumption. So this is LW, and the ciphertext is based on Sept assumption. So you can do combination of this. You can, so I think the best way is to base the public key by LW, but also ciphertext as LW assumption. So you use two LW assumption everywhere. So that gives you the type of small parameter.
Is there a
Region-based, right?
So regave gives a scheme, but there's also something called dual regave. I don't know which one. Yeah, I don't know which one is called dual regave and which one is called regave. I forgot the name, but one of these is originally proposed by an early paper by regave.
Is there a relation between the SIS and the downside of the problem?
LS, yes, I think there are the trivial reduction. So you can reduce trivially from LW, can trivially reduce LW to this, I think. Right. So this is a classical algorithm, right? And recently I learned that there are also reductions from 6 to LW, but this is a quantum reduction, I think. Yeah.
It's interesting because for codes, in fact, the reduction is trivial in both cases.
Yeah,
If
so
you exceed on the coding
Uh-huh.
and the decoding problem, like you can
Yes.
go from one to the other with the dual, yeah, essentially. So
but does that involve a parameter change or something like that?
it's
Okay,
really, well,
okay,
you maybe have to change the dimension by one.
okay,
It's really
okay,
the same problem.
okay, okay. Okay. Interesting. So what is the main problem for that scheme that I just mentioned? If you compare this to RSA or discrete logarithm-based scheme, the main problem of lattice-based scheme when started is the size. The reason is in RSA or discrete logarithm, usually the ciphertext is just one or two field elements. So if you think about standard parameter for RSA, for example, you need 2048 bits for a single element. Basically, it's really just you just say, for example, you just transmit two elements. Each element has like 2000 bits, right? So and therefore the public key, the ciphertext side or signature side is really a few underlying field element. However, in lattice-based crypto, for it to be secure, like the example I mentioned, consider the public key like the A and the T. They have to be matrices of big dimension, for example, 1000, right? And even if the modulus or the underlying finite field is really tiny, you still have to record, let's say, 1000 times 1000 entries of integers. Each of the integers is modular P, right? So that's about 1 million times the underlying bits for this P. So therefore, the main development to make this lattice crypto practical is how to further reduce the size, which is to use this algebraically structured lattices. And I'm going to, because of the time, I'm just going to focus on a single one, which is called N2, where I started with some cyclotomic polynomial, and I consider really the X model of this cyclotomic polynomial. Okay, so where n equals to phi of m. When we usually consider the case where the order of the cyclotomic polynomial is the power of 2. So I have a very nice form for this by m. Usually it has power of x of 2 to the k minus 1 and that plus 1. That's the general form for cyclotomic polynomial. You can quickly search Wikipedia to see this shape of this polynomial, which I cannot remember the general form if it's not about 2. Okay, so the key generation for N2-based encryption it's slightly different to the LWE problem because it's a different assumption, but it's very easy by how it looks like this. For example, I generated two small polynomials from the ring. Essentially, they just mean that they have each of the coefficients is small. It could be ternary or binary polynomials. And the public key is H equals to G divided F or GF inverse modular Q. So this F inverse is computed modular the Q. I'm assuming that it's inverse this, so because we don't have a field there. Okay. So the untrue problem is essentially to given H recover G and F, so which are small. So if there's no restriction of GF, then on the size, then the problem is easier because given H, you can take any uniform G and compute F by doing G divided H. That give you the F, which is also uniform. So the main hardness again is the constraint or restriction on the size. So there's a requirement that you have to make sure that G and F are both small in order to break the system. Okay, and that's exactly the untrue problem. Okay. I'm going to give example just to show numerical example just to show how the loop works. And it's based on stage math. So if I take that ring, R equals to ZX mod X4 plus 1, I'm going to take Q to be 1,000. Actually, this Q was quite close to what we use in practice because in the entry-based scheme or in general in the lattice-based encryption scheme, the underlying field usually has very small size. Signature we do have a slightly larger size, but for encryption scheme, usually the Q is smaller. However, this parameter was not practical because for this to be secure, I need to change it for to be something like 500. Okay, so that's and now I can define all of this in sage math, and I get the two random elements from underlying field. So instead of define the ring, I define a psychonomic field, and then I took two elements actually from the underlying atomic field, and these are the two polynomials. I assume that this implies that they are reasonably small because the coefficients are just 2,5 minus 1,7 compared to this Q. It could be binary, okay? And then the main trick is if I compute H equals to G over F, you can see that my G is small, F is small, but if I divide them out, somehow this coefficient becomes large, right? Compared to the underlying modulus Q, which is about 1,000. And that's really where the hardness comes from, okay? And you can double check this by moving F. You can multiply, this is my H times the secret F, it equals to G. Actually, check that, which is the step given here. So in matrix form, I can rewrite this. I'm just doing a very slow way by opening this symbolically. But if you have done algebra, you know that this exactly corresponds to the multiplication matrix of element for the field. You can rewrite H times F by you can expand this way, and then you can rewrite this as a matrix form. And believe me that this that corresponds to this one. You can rewrite the polynomial multiplication into a matrix which has some structure and times this F, and it equals to this one, this equals to G. So the most important part is this H, because H corresponds to public key, and you observe that there's some pattern over here. So basically, its entropy is lower than before because you have H0, H1, H2, H3, and in the next column, you have H0, H1, H2 minus H3. So you still have the same element up to a sum, right? And in this way, you don't have to store, let's say, n-squared elements. You only have to store a single column. This is a general trick to save memory, to save the space in lattice-based crypto. So we always have to stay order n samples as opposed to order n squared samples. You can define something similar for LWE, which is so-called polynomial LWE or ring LWE problem using the same trick, and that reduces the order n squared matrix into order n. But clearly there is a problem for doing this because we are changing the underlying problem, right? Previously, the problem has no structure, no algebraic structure at all. But after we did this trick, we are imposing or we are adding an algebraic structure to it. So the problem is, the problem is, does the problem with algebraic structure admits the same security as the problem without any structure? So that's an ongoing research problem, actually. Actually, in all the NIST standardized scheme, there are algebraic structure for this, for lattice-based candidates. All of them have some algebraic structure. Okay, it took a lot of time. So I'm going to have a summarizing for this. So we talked about the encryption, whether you can construct all of this into the functionality. For example, you can do the signature, and there is a hash function. What is nice is you can use it lattice to do some advanced functionality. For example, homomorphic encryption, which is the topic of one of our reading series for the crypto group. It usually happens every other Thursday other than the crypto Café. And there are more advanced schemes which I'm not expert on this, but there are obfuscation and multilinear maps and some functional encryption that you can do using lattice. Okay. All right, so that's all I have. Okay. Are there any questions? Yeah.
Actually building this intermediate obfuscation, or is this like a wish from the start?
There are some proposals, and some of them got broken. I'm not an expert on this, so I don't really know the current status of that. Actually, I think they built. I think now there's a trend to build this from code-based assumptions like LPN and the other stuff.
I've seen this trend.
Yeah,
but
yeah.
I usually don't think LPN is code-based.
Okay, yeah. But in any case, so yeah, there has been attempts, I think, of building this high functionality. But for homomorphic encryption, there is indeed a big trend of using lattice. Yeah. Yes.
When you really introduce these rings, ZX modulo,
Yes.
the tectonic going on. Why? But you implement them with the tectonic field. Why don't you directly talk about the integer ring or the tectonic field and then introduction of the two and this kind of thing? Why you not directly couch that in the language of?
So you're saying we start with the QX model like 1+1?
No,
We start with
just R the ring of integers of the tectonic field, and then the Q just reduce modulo 2.
Yeah. So that's equivalent for the case of second one. I think the only difference is if you don't have the case where you have the maximum order equals to this form, the real integer does not equal to this form, then you will have different notation, right? Yeah. So I think that's correct. Yeah. I can just say that you're right. I can just say that for this specific case, I can just take R to be the real integers of the underlying cyclonomic number field. You're right. Yeah. Actually, that's the only case people use, I think, in practice. There are some other proposals actually.
Maybe because there were other things where R was.
There are other things. Yeah.
Not
Yes.
a domain, but like a product of like the modular polynomial was not reducible.
No, so so if you think about the R mod Q over here, if you do the R modular Q here, you don't naturally get a Q. So if you replace it V by Q, you get a cyclonomic number field. However, if you take R equals to the real integer of that and then do a modular Q, even this Q is flat, you don't necessarily get a field. Usually what you get, actually almost always you get a product of this for example of this n where n is degree number of linear factors in the factorization because people want to use NTP. So we don't get, like what you said, we don't get a field, we get a product
yeah, it depends if the prime splits or not.
Yeah, we usually get a product of five fields. Yeah.
Okay. Thank you for the time.
Okay. Okay, thank you. Let's just do it.